Hello physics students, this is Dr. Berenzi and this is lesson 8.2.1. I'm using some new software to do my recording today, so it's not going to look like one of my user recordings. I won't have as many options to read on the screen, but I hope this video is nonetheless effective and educational for you. So our objective for this lesson is that we're going to be able to calculate the potential energy of a charge in an electric field. Let's skip that, and let's talk about work and potential energy. So we're going back to Unit 3. In Unit 3, we learned that a force does work when it is applied along the direction of motion. So you see a guy over here on the left, and he is pushing a fridge. So he's applying a force directed towards the right, and the direction of motion of this fridge is also toward the right. So we can say that this force that the man is applying does work on the refrigerator. And we know that that work results in a change of the refrigerator's kinetic energy. Whoops. I keep on going back to the slide. Sorry about that. Whoops. All right, some glitches with the new software. Now, we also learned about the idea of conservative forces. And that is, a force is conservative if the amount of work that this force does only depends on the beginning and the end point. In other words, if this force is conservative, then the amount of work that the force does on the fridge only depends on where it starts and where it ends. Okay? So if our refrigerating moving guy pushes this directly from this point to this point, he will do a certain amount of work. And if this force is conservative, if he takes a different path, like say a crazy winding path like this, and ends up at the same point, well, if he does the same amount of work between those two different paths, the straight path and the crazy curvy path, then this force ends up being conservative, okay? Because the amount of work it did only depended on the beginning point and the end point. It didn't depend on how he got there. Now, we know that conservative forces can be assigned a potential energy at any point. So I can say that the potential energy of this force right here is some value. Let's give it a value x. Let's give it a value e. So let's say E. And then let's say that this the potential energy here is E2. So let's say E1, E2. Okay. So I can actually calculate the amount of work that this guy does on the refrigerator by simply taking the potential energy here, E2, minus the potential energy here, E1, and I will get a value of the amount of work that I did, or the amount of work that he did, excuse me. And that is, that's very commonly what we do when we have a ball that is a certain height above ground. So let's consider the bottom of this slide the ground. And let's say that I have a ball that's height above the ground. And I know that I can assign this position a potential energy of U equals mgh. And then as it falls, gravity does work on the ball. And if I assign a potential energy of 0 to where it hits ground, then I can calculate the amount of work that gravity did on this ball by figuring out the potential energy here minus the potential energy there. And that gives me the amount of work that gravity did on the ball. So when it gets here, I can figure out how much its kinetic energy changed when the ball hits ground. Well, the big question is, now that we're dealing with electric force, can we assign the electric force a potential energy at every point in space? Well, first of all, we have to know, does the electric force do work on a charged particle? And we can say, yes, it is a force along the direction of motion, so it does work. After all, if we put a test charge, a positive test charge right here at this point, we know from the electric field diagram that that charge is going to follow this electric field line from positive to negative. And it's going to gain energy as it does so, because if I started off from here at rest, there's a force being applied to it, so it's going to want to start to accelerate. And that means that we are doing work on our charged particle. Now, the second thing we have to ask, is electric force conservative? Well, in order to answer that question, I would have to get into some pretty, I'd have to get into some calculus, or at least provide an example, and I don't want to have to do that. But if you want me to demonstrate that to you personally, I can do that. But let's just suffice it to say for this video that electric force is actually a conservative force like gravity is. Okay? And as a matter of fact, we're going to find out that electric force and gravity work in very similar ways. So we know that it's a force that does work. We know it's a conservative force. Therefore, we can say that we can assign a potential energy to this little charged particle anywhere it resides in space. So no matter where I put this charged particle, it will have some sort of potential energy U that I can assign to it. Okay? Now, in order to give you a general idea of what electric potential energy would be for like any given situation, that would involve calculus, and that's obviously beyond the scope of our course here. But I can give you a couple of interesting cases. So case number one is when we're dealing with a single point charge. Now, in order to kind of help you wrap your head around this, I want to actually talk about gravity. In Unit 6, we learned that the gravitational force between two masses, a big M and a little m, if they're separated by a distance r, we found that the force of one mass acting on the other is equal to negative g big M little m divided by r squared. Okay, that's Newton's law of universal gravity. We also discovered in Unit 6 that the potential energy of this little mass at any point in space only depends on the distance it is from the other mass. So its potential energy at a given point in space is given by negative g times big M times little m divided by r. Now, let's talk about electric force and see if we can come up with electric potential energy. Well, we know by Coulomb's law, we learned before spring break, that the force between two charges, Q1 and Q2, is given by Coulomb's law. So F equals K, that's Coulomb's constant, times Q1 times Q2, divided by R squared. And we know that looks very similar to gravitational force, and in lesson 8.1.1, we learned about the similarities of those two and just how similar they are. So, if you were to take this force, what would its potential energy be if we know that this force gives this potential energy? Well, it turns out that the potential energy in an electric field between two charges, Q1 and Q2, so if I were to take Q2 and if I were to move it around, what would the potential energy of that charge be at any point in space? It would be given by this equation. It's K times Q1 times Q2 divided by R. R is, again, the distance between the two charges. So the amount of potential energy that this charged particle has due to the electric force only depends on the distance between the two charges and the magnitude of the two charges themselves. Just like gravitational potential energy only depends on the big mass and the little mass and the distance between them. So now we can use this formula down here at the bottom right to calculate the amount of potential energy that a charge Q2 has in space when it is being attracted or repelled by a charge Q1. Now let's consider another case. Let's consider a uniform electric field. Now, I want to draw your attention here to the top right-hand side. Okay, we can create a uniform electric field when we have two equally charged plates, one positive and the other negative. And we learned before spring break that the electric field is uniform between these two. And we also learned that it is pointing from positive to negative, so we can say that a uniform electric field is like the electric field that gets created between two charged plates. Well, is there a gravitational equivalent? The answer is yes. Well, it turns out that the gravitational force, when you have a ball that is a small height above the surface of the Earth, it also has a force that is uniform. It doesn't change. Now, I realize that I just forgot to tell you about force in this electric field. So let's come back to this over here. The force on this charge Q inside this electric field is given by this formula. It's just the charge Q times the value of the electric field. And since this electric field is constant, that means that this force only depends on the amount of charge that our little test particle has. Well, in a sense, the same can be said of gravity. Okay? Gravity has a force when you are talking about a ball that is near the surface of the Earth. Its gravitational force is equal to m times g. Does that change if I move the ball from here over to here? The answer is no. It stays the same. Just like this electric force doesn't change if I move it from here to here, or from here up to there, or from here down to there. It is still going to be this constant electric force that only depends on the amount of charge. This force, the gravitational force that we know and love, only depends on the amount of mass that this ball has. So these two, this situation is the equivalent of this situation for electricity. So if my force is equal to m times g for the case of gravity, we know that the potential energy that we can assign to it only depends on the height that this ball has above the ground. So we can say that U equals m times g times h. Okay. If we go over here to electric force, in this situation, well, what would the potential energy be? It turns out it's going to look similar to what we came up with gravity. The potential energy of a charge in this uniform electric field is just going to equal the electric force times a distance d. Well, somebody wisely asked, well, actually, I asked you this in class, and I said, well, what is d? And somebody answered, well, it might be the distance between these plates. And then I answered, well, it's actually the distance from here to where it's going to end up, which is actually at this negative plate if we have a positive charge. Now, I didn't put it in exactly those many words because I was a bit rushed during class today, and I wish I had answered this differently. So that's why I suddenly blotted this out, and I want to talk to you about how should we treat this D and what does it mean. So let me give you a couple of examples here, and these examples are going to help you with the practice problems anyway. I didn't give these to you in class in great detail, but I want to give these to you here now. So let's take a look at an example of a positive charge in a uniform electric field. So let's say that we're given an electric charge of, or electric field, excuse me, at 20 newtons per coulomb, and it is pointing downward, just like in our diagram. And we are being given a positive test charge Q, or a positive charge Q, which is positive 4 coulombs. And instead of talking to you about the distance between this place and some plate down here, we very often are just given the electric force, or the electric field, excuse me. We're just given the electric force or electric field. God, I keep on saying that. We're given the electric field, and we're given how much distance it moves in that electric field. So very often you don't even know where these plates are. But we can still use potential energy in order to calculate the amount of work done. Because the amount of work done, and I'm going to point you down here first, the amount of work that this electric field does on this charge Q is delta U, the change in potential energy, which is equal to Q times E times its change in displacement along the electric field. So, if I wanted to calculate how much work was being done on this charge by this electric field, I would multiply Q times E times its change in distance, or its change in displacement. So I would multiply 4 times 20 times 2, and I would find out that it has done 160 joules of work in that amount of distance. Now, one note of caution. And this is a note of caution about whether you have uniform electric field or if you have any electric field, actually, is that the change in distance is positive when the motion is along the electric field, okay? So this positive chest charge is going to move down along this electric field, so the electric field is doing positive work because there is a positive displacement. So this displacement is positive because this motion is along the electric field lines. Okay. Now let's consider a negative charge in that same uniform electric field. We know that a negative charge is going to go in the opposite direction of the electric field because we know that positive charges go along the electric field lines and negative charges go against the electric field lines. So if I, again, have an electric field that is pointing down and its magnitude is 20 newtons per coulomb, this negative charge, negative 4 coulombs, is going to be pushed up by this electric field. So how do I treat that with as far as calculating the amount of distance it has traveled? Well, actually, since it's going against the electric field, I actually have to use a negative displacement. So my delta D, that's the amount of displacement, is negative when the motion is against the electric field. Now, why do I have to do that? Well, if we use our formula, again, to calculate the amount of work that's been done, we will take Q, which is a negative number, times E, which is a positive number because it's a magnitude, and then delta D is negative since the charge is going against the electric field. So now I have negative 4 times positive 20 times negative 2, and that is still going to give me a positive result. So the electric field is still doing positive work, positive amount of work on this negative charge, even though it's going in the opposite direction. Now that is a big difference between gravity and electric field. Electric field, it treats electrons differently than protons. It treats positive charge different from negative charge. This one electric field is going to push positive charges down, but it's going to push negative charges up. And in both of those cases, it's doing positive work, okay? The amount of kinetic energy in a positive charge is going to increase, and the amount of kinetic energy in this negative charge is also going to increase even though it's moving in the other direction. And that's why we have to keep careful track of our signs here and then use this convention that displacement is negative when motion is against the electric field. That way we always get a positive amount of work done by the electric field, and it doesn't matter if that electric field is pushing a positive charge or a negative charge. Okay, now I know that's a lot more detail than what I gave to you in class, so I hope especially these last couple examples are very helpful for you. And I look forward to seeing you in class tomorrow where we can discuss this further. Bye.